information about building a modern internet exchange.
So am I the last guy before the beer, or is it one more session? Or you hear me now?
Yeah,
right.
That's better. No, you're not. You're standing between the coffee break.
Oh, thanks
so
for that.
Thankfully, you
All
have
right,
the
all right,
time.
okay.
Relax.
okay, good. All right. Peter, can you close the door?
Can someone close the door? Thank you.
All right. Hi everyone, my name is Peter Lundqvist. I work in Arista Networks. By the way, I have two of my colleagues down the hall there in beautiful blue shirts. It's Peter Kotilas and our Danish masterpiece Klaus. So any questions, I refer to those guys. I'm just a lying son of a bitch here. I'm gonna talk about, how many of you guys saw Rory's presentation next hall? Raise a hand. Good, so this is sort of a natural implement what he was talking about, right? So now is the proof of the pudding. Of course, I come from a vendor, but I try to be sort of neutral. When I kind of gonna share, hi, what I think sucks and what I think everyone likes. That's sort of my trademark. I'm not gonna be as polite as Hugge, however, so don't, relax. So, oh shit. IXP, simple thing. Lay 2. You're a band-aid for connected peering. So you're going to connect routes to each other so you can exchange, and essentially you can get internet working. It's been a very successful subject and a successful story for many years. They've been built in many years, but essentially it's very simplified, right? So what you do is that you provide a port for a reasonable charge. Sometimes people maybe give them free, but ultimately you will have to be paid for it. And you will get a prefix. And you go to a somewhat most certain to a road server, and that's it. Then you start peering to each other, and most hopefully some music will happen. There can be different services. There can have different MTUs. It can be IP version 4, IP version 6. Of course, you can't have a session without saying IP version 6 these days. And it could be multicast, right? But that's pretty uncommon. And that's it. It's interior, very simple. So why do you want to waste 45 minutes on that? Well, I'm going to try to make it complicated because I come from a vendor. Not as complicated as Julian and Juniper because they make stuff very complicated, but I'm going to make it decent complicated because I have to make my salary. So IXP is a band-aid. That's it. It's nothing else, right? You guys could do private peering to each other and all that stuff and try to make friends with each other, but IXP is sort of an easier way of making internet growing and working. That's it. And it is a successful stuff. It's been going on for forever and ever, and you have NetNode and you have Stockholm Exchange here, so they can talk all about it. And there's a whole bunch other of EXPs here. So that's the proof of the pudding. Very fast, if you are successful, you're going to grow. That means that you need to build somewhat of a fabric. Then it gets complicated. If you only have 1 or 2 switches, it's not complicated at all. When you're growing, that's when it gets complicated. And growing in a network is complicated in any type of network. It could be a data center, it could be a WAN, it could be optic stuff, right? Growing a fabric, that is when you get a thick skin on your nose. So this is what we're going to talk about. How many here know about Arista? Raise a hand, please. How many know about Arista records? Raise a hand. So apparently there's a music company, and I actually got 2 calls from someone that want to hand over their tune. They get a contract, and I apologize, but I'm not into that. Even if I look like a rock star, soon I'm gonna get my tattoos like Huggy and then be a really important guy on the internet. But so what we do in Arista, we build data centers. We build absolutely the biggest data centers in the whole world. And we claim to be doing it pretty good. Because I know everyone in here, maybe you don't have Arista equipment, but I bet my salary that all of you has passed Arista equipment today. Because you have your Facebook, if you have Spotify, if you have Google, you have passed our gear. So don't piss me off now, then I'm gonna make your life horrible. And you can't have cats on Facebook and stuff like that. So why are we building an exchange point chart? I mean, if we are a data center, well, we have learned some stuff really, and those stuff I can try to share, and then I'm gonna jump more into the IXP design. First of all, this is the design that we trust: leaf and spine. We don't build fat trees. We don't build circles. Actually, we build only this design. This is called leaf spine. This means that you create an isolated spine where leaves get connected. So you can see here there's no link between the spines, right? We don't try to create a fat tree. If one of the spines fall down, good. Sad to say. So in this case, I have three. Let's say I have 3 spines. So if one of the spines fall down, it's unfortunately 33% of my bandwidth has gone down, but I still have 600% of the connectivity, right? So leaf spine is what we build, and these are the lessons we can apply to Internet Exchange Point also. We build them in a standard fashion. We don't do any clustering. We don't do any proprietary stuff. We don't create an I-size database and announcing MAC addresses and call it a feature. Are you ashamed for your I-size, right? We don't build hide BGP and announcing MAC addresses. No, we use routing mechanism. I prefer we use BGP, but I'm gonna spend a lot of time on that. Second rule is layer 3. If layer 2 would have worked, it comes and goes, with the circuit connect internet and the layer 2 and LAN emulation and all that stuff. They keep on trying. In the end, why we have internet is because of layer 3. So we believe in layer 3 fabric. Layer 2 works best at the edge. That's leaf. You should never leave that. For onward, it will be an L3 packet. So in the IL design, you have, in this case, only layer 2 aware, the VLANs. They only exist on the leaves, not in the spine. Multipathing, that's the name of the game. This is where you marry essentially convergence and performance. What is the best redundancy? Active, passive? You can bet your sorry ass that your passive will not work once it needs to be active. So multipath means that every link is active. Every link is used. That means when you're buying a switch from me, that one earns its salary, right? You don't buy a bunch of links just to push traffic on one link. So ECMP in an ECMP cluster in a leaf spine, that's crucial. If you haven't managed that, then the whole model is gone down. Then you have a circle or anything like that, and you can't have that. So now it goes to a little bit of religion. What protocol to use? It is tempting to enable a link state protocol. You just put everything into one CLNS layer 2 only domain or OSPF. It will work. It perhaps can be a little bit easier to do automation on. But it is not designed for a leaf spine architecture. If you would enable link state protocol, you are slave under the protocol's design itself, which means that everyone needs to have the same database, which means that you need to have flooding. So when this fabric works at best, that is when everything is stabilized. So during a certain, let's say that you're breaking a link, you can have undesirable flows, where essentially a leaf, spine, leaf would occur. Because of the simple fact that some of the nodes here had converged faster. The flooding of the LSP or LSA, depending on what link state protocol, has converged faster. That is the drawback with a link state. I saw that Rory saw that they are more complicated to troubleshoot. Yeah, I could agree to that, but it is essentially a database, right? So you can also say that if I have everything in the same database, if everything looked the same, fine, top notch, then everything should work, right? The thing with link state database in a data center and leaf class is that you can have unpredictable flow when the link's going up and down. And even if you have the most stable as NIC, even as the most stable operating system, failure can happen. SFPs, QSFPs can break down. There can be some heating, which means that some lasers where you haven't, what did you do, Hug? You washed them with your whatever. They could be dirty, whatever. So you could always run up into flapping links. And this is where you can run into these scenarios. So what protocol to choose? BGP is the name of the game. That uses BGP. Why should we use it in the data center? It is very predictable. BGP doesn't have a concept of database. It has a concept of a local RIB, which is a calculated table for each node. But it also has an agency, calculated RIB, what it receives from everyone. So if the left-hand side link goes away, it already had calculated a determining path on the right-hand side. It doesn't need any flooding. The flooding will occur because this guy doesn't have a route any longer. But it doesn't need to have the same database to have consistent forwarding. BGP also has some other cool things, right? Is that if you peer on the link and you at least have 10 gig, if you receive goes down, then the TX also, right? So you could actually get away with actually not running BFD. Most of the cloud operators don't even have BFD on the session. Still, they have convergence way below 50 milliseconds. So this is absolutely the most common design is that you're using proprietary IS number, 2 byte to 4 byte, doesn't matter. And each leaf has a unique AS number, but the spine has the same. Because the spine, they don't have any BGP session to each other. They're never going to talk to each other. They shouldn't be aware of each other. This is absolutely the best design. This also means that you have perfect tracking because the AS path will tell which they have prefix, it belongs to this leaf, pass on this spine, and so forth. So you have excellent tracking for where your prefixes are in your data center. You don't need to have communities and stuff like that. There is a simplified design if you really hate having lines or you have failed in your automation. Then you can also run this, which means that you have all the time the same AS number still on the spine, but they also have the same AS number on the leaf. This is a loop. This is inconsistent. The other loop that knows BGP. You fix that by allowing it that you can see OMI's path 2 times in the path. This is also very, I would say, common in the finance space. I don't know if they have lack of auto provision or they are lazy. I have no clue. But this is also one of the design how to do it. Still, we need to comply to the BGP rule set, right? So in order to have the perfect load balancing scheme, according to path selection, you need to, the attribute needs to be the same down to multipath. Once it's down to multipath, glorious things will happen. Because then you're kicking multipath. And now you have an ECMP architecture. So in this case here, I had 3 paths. And if I turn on multipath, these are load balancing paths. And now we have built my perfect fabric with a 3-time load balancing spine. This is absolutely the most common design about the cloud titans and essentially all the databases, all the data centers that I built. This is absolutely the most common way to do it. Right, so now it gets back to the reason why I'm here and talking about IXP. So I'm not going to talk about the layer 2, obviously, right? Spanning. How many of you guys are good in spanning tree? Peter, fuck off. I mean, you don't even remember what you had for breakfast. How many of you guys like spanning tree? So obviously, I'm not going to do that, right? And one of the reasons is I'm sucking in spanning tree, right? Also, so I'm they always when I'm presented, there always are someone, and it's even older than me, and he has a bird or something like that that claims that he can build and scalable layer 2 spanning tree-based network, right? So there's always someone. Hopefully, he writes a book on the matter so he can get some money because he's not going to get any job past in 2018. Then the next thing is what control plane to choose here, right? So we can make it complicated and we can make it easy. So I'm going to grasp through that. So this is a spanning tree exchange point, right? One way or another, even if you do a leaf and spine, or in this case, a poor man's triangle, this is the perfect loop for layer 2, right? You need to have a breaking point. This is what spanning tree is doing. The only one that is happy with doing this is vendors like me and Peter and Klaus, because we force you to buy links that's not in use. So those links are they're absolutely for no use whatsoever. They're not going to be used because they need to have somewhat taking care of your loop protection. So it doesn't matter if you're on an MSTP or PVSTP or whatever STP. The only thing that you can have, you will still have a blocking link somewhere in a calculated bridge domain. Doesn't matter what spanning tree protocol you use, it will be a block. If anyone can show me a spanning tree that sort of solved the perfect load balancing by blocking one VLAN and forwarding another, and you still have it growing, send me an email and I will buy you some good wine. Some Swedish wine, they suck and are cheap. The next design is try to avoid the triangle, right? That means that you build an A and a B side. Essentially building two networks, right? And you're forcing the clients here to dual home connect. Then this will work. This will actually work perfectly. It's just one little bit problem here, right? You're paying for an extra hardware here, right? So again, me and Peter and Klaus are happy. So what to do about it? Well, we need to have an overlay, and sort of the new kid on the block is VXLAN. VXLAN was intentionally not designed for this. How many of you guys know about L2TP? Raise a hand. If you know L2TP, you know VXLAN. Simple as that. I'm going to talk a little bit about mumbo jumbo here, right? So building a VXLAN, there's one thing you need to, actually two things you need to run. VNI, and think VNI as VLAN or stack labels if you run MPLS. That's the same shit. You're mapping a VLAN to a VNI. Another attribute is the VTP, the VTEP. And that's the source address of your switch. It's nothing else. Because if it's a source address to me, it's my destination to Klaus, right? So this is how you create the tunnel. And then back to VXLAN. VXLAN is not a GRE header. The reason why I'm saying L2TP, because what's so special? What's the difference between L2TP and a GRE? GRE is always up, right? In the kernel, it sees as an interface. So you usually put an IP address on it, right? That means it's a tunnel that is always up. VXLAN has no such concept. It's a shim header, very similar to MPLS. So if I now send a packet in a VXLAN encapsulated to the front row here, it will have one source port number. I am the same source, I have the same MAC address, and now I send a packet to row number 2, which means a different session, right? Now the packet will have a different source port number. So the VXLAN is created on the fly. VXLAN is created when you need to tunnel something. That's why it scales pretty good. Because if it would be a GRE, it's installed as an interface into a kernel, and you end up something like 4,000 interfaces at most. This is the big difference with VXLAN and, for instance, GRE. Very good thing with VXLAN is the creation of the source port number. It's a UDP packet. The destination port will be 4,000 something, 4,079 or something like that. The source port number will be calculated based on the data you put into the VXLAN tunnel. And that can be a combination of source and destination MAC address, or if you have a more mature platform that we have, it's based on 5 tuple. So even if it's sort of a layer 2 technology, the hashing of the layer 3 on the ingress VTEP, he will calculate when he ships the packet with a different source port number. What's good with that? Load balancing. Because if he passes a spine or passes 2 or 3 nodes to the ultimate egress, session will be different according to 5 tuple, right? Because the source port will be different. And this is also a big difference to a GRE tunnel that is always up. I mean, what's bad with MPLS? MPLS load balancing like shite. And that is because the stack labels is always the same. The outer label swaps on each link. But in order to have 5-tuple load balancing, you need to read very, very long into the packet with complex ASIC. That's how you're going to load balancing, right? That's the problem with MPLS. Elsewhere, it's a perfect technology. You don't have no such problem with VXLAN. So this is how it looks like. MAC address get back to a VXLAN, and that's it. In ASICs from Broadcom or from Intel or whatever, there is no significant performance impact if you baseline adding a Q tag or a VXLAN header. This is done in the hardware. This is done in the ASIC. This is done in the line processor. There's nowhere in a modern implementation is the CPU involved. Early days, an immature VXLAN implementation, then the flooding occurred on the CPU. But once you have it on the forwarding, then this packet is created down on the chip. So Broadcom and other vendors, they have done a very good job so that this is perfect. This has line rate that you can go. Of course, there's a penalty in that sense that you will have a UDP overhead. You can't, that's nothing that you can fix. But those problems you had with MPLS also, right? So this is the only real impact. So you can baseline a mature implementation, and you will see that baking in the original packet in an IP packet, they will not have significant worse performance. Actually, you will not be able to measure it. It will down to maybe 1 nanosecond at most, compared to if you have a simple VLAN tagging. Very few people actually test that when I'm staking it, but one day someone will do it. So now to the control plane, and here is what we vendors really doing our best to complicate things. So Arista is mastering and have a whole bunch of control plane here for distributed VXLAN. Because VXLAN itself is not a control plane protocol, it's a forwarding technology. It's just to bake something into a tunnel. In order to find out the VTEPs to begin with, you need a control plane. And also, if you want to have some automatic scheme in adding your float list, you also need a control plane. So it records still according to RFCs. Multicast is the preferred control plane. That goes with saying is that multicast is used very little in the concept of VXLAN. It's used in the flooding. When a switch doesn't know where a MAC address is, what does the switch do? It floods, right? So with a multicast VXLAN plane, you will flood the ask, where is this MAC? The VTEP that answers, I have it, because it answers actually with learning, which is its response. Then it programs into the forwarding table. So any other forwarding here will be unicast. So multicast here is only used for the flooding discovery, right? For the learning process. Has nothing to do with actually forwarding. Another way of doing it is doing OSDB way of doing it. That is, if you have an extensively advanced, for instance, VMware network, VMware NSX is using only VXLAN to be able to communicate. Then we have features that we knock ourselves into the VMware NSX control plane. So the NSX, for us, we as a switch, we just look like a vSwitch to them. And a third way of doing it is to use advanced feature set like Evpn. That means that you don't do flooding. Instead, you advertise the MAC address in the BGP packet and the VTEP flood list. So it's sort of VPLS all over again with a little more niche. And the last alternative is that you do a header replication. And that is just you've defined your static flood list. And thereby, you send to those guys in that flood list and ask them where is this MAC address. And the response then will be a learning. I will come more to that. So let's look at Evpn. This is one way of doing it. You have build your BGP leaf spine, and then you have multi-hop BGP sessions between the leaves. This means that the spine doesn't have any knowledge about the address family of Evpn. That BGP session just flies over it. So you have configuration-wise BGP for your underlay discovery, and then you have BGP for your overlay. Another thing is if you're running on the same operating system and all that stuff and you trust the code is good, then you are lowering the spine to also be aware of the Evpn address family. then you only need one BGP session, right? Because you will learn both your underlay and your EVPN stuff through that BGP. So this is one example of it. Not going to go much more into it. There's a lot of stuff that goes over the wire in this stuff. So this packet is to learn in the type 3. This is essentially the flood list. So here he sees that, okay, this is how I learned that 223 is actually a VXLAN egress node. And once you're happy with that, this is how it looks like. So now we have all of, how many guys here are very fluid in MPLS, L3 VPN? This is the same stuff, right? So you will be happy. And the ultimate result is that you have a very advanced RIB here, where you're mapping VTEP to MAC addresses. I don't say this technology is bad. Absolutely not. I've been this has been my work for 14 years when I was in Juniper and building MPLS with stack label services. I mean, there's nothing wrong with this, right? But from an exchange point, really? Do I need to have VRFs and build up a community plan and all that stuff just to make, let's say, 500 MAC addresses learn each other? Who wants that? Yeah, perhaps I want it, right? Because then I can, charge you a more expensive license, right? But that's it. So an alternative is doing this. This is hidden replication. This means that you specify the VTEP's flood list statically and the VNI to VLAN mapping, and then that's it. And by the way, if you do an auto provision, this is a dream, because the same configuration is in all your switches. Exactly the same. It doesn't matter if your own address is in the path, because it's not going to flood to himself, right? So if with this tiny configuration, and if you have built a BGP underlay, you're all set. Now we have reachability. And by the way, the output is pretty nice, right? Because you can actually map a MAC address to an IP, right? It's pretty hard elsewhere to see that if you have a spanning tree network. Then you have to jump around. Regards to loop control, this is a classic split horizon case. That means that what you learn from VXLAN will not be forwarded back to another VXLAN tunnel. So if a packet comes in from a VXLAN tunnel, it will only forward it out on that VLAN on the access port. And that's a dream. That's the easiest way to prevent loops, because VXLAN is a full mesh technology. For instance, when is spanning tree good? Every cloud guy should say, we don't run in spanning tree. They lie. They run spanning tree local on the switch, because what fix it? Because usually they have someone else to do the patching for them. So they say, please, Ethernet 1, can you move that Ethernet 2? Guess what link they will move, right? They will not move the link on the switch. They will take it in a patch panel like that, and then nothing happens during that day in that VLAN. But if you have spanning tree, it will only be on that VLAN on the switch. It will not saturate every stuff that you have on the switch. So, but no spanning tree is forwarded over VXLAN technology by default. You have to explicitly state that you want it, because it has really no sense of it either, right? Because it is a shim header, it's not an interface that's up all the time, right? There is no point to see the VXLAN as an interface in your topology. The layer 2 loop detection, if you have the bad taste of building a layer 2 network further down from the leaves, then build your spanning tree. But the spanning tree by default will not be forwarded into the VXLAN. So what is flooded? It is your ARPs. It is your V6 discovery stuff. That is what is flooded, because that gets the network going. Then it's the same as any other exchange point. You apply your same access list or the same filtering or whatever you want on the ports to protect that something nasty is going to happen from your customer that maybe connects wrong or something like that. Nothing that has changed in this type of setup. So, any question? Am I boring? Peter is saying yes down there. Thanks for that. So how does ECMP work? So let's go into more practice here, right? So let's imagine that you have two links here, and you're running a VXLAN protocol in between there. Regards to load balancing, if you fire up BGP, this is how it looks like. You will essentially have a load balancing path to the VTEP address, right? Everything will be encapsulated. So if we're rolling back again here, On VTEP 111.7, apologize for not typing in V6 addresses here, but I'm lazy. So imagine there's a CC dash something, so it's a V6 address. So everything here we encapsulated, so the destination for the VXLAN packet will be the VTEPs, right? So this is very load balancing, right? So if you have BGP peering on the links, they will load balancing, the route is learned, in this case it is the loopback address, which is the VTEP. So here I have a simple connectivity between two hosts. They have the same MAC address, right? So first I think I do a SSH. You will see I have a port number 300338 something. And then I do a telnet, fancy protocol, right? 56263 will then will be the source port number and so forth. So it's not MAC to MAC, right? The port number that is created in the VXLAN is based on the 5 tuple that I shuffle into it. Another problem is, in the best of world, you have the same speed, right? So all the links between your leaf and spine, they should be the same speed, right? But there could be some problem there, right? Maybe you don't have all 100 gigs or 40 gigs, so maybe you do some bundlers on 10, and one day someone knows are breaking down because Peter has sold a faulty SFP or something like that. That can be fixed. Because with BGP, you can do glorious things that is a pain in the butt to do with a link state protocol. And one of them is that you can apply a weight. And that weight applies to the forwarding table. So in this case, I have a 10 gig interface and a 100 gig interface, and apply a weight, because my purpose here is that I want 10 times more of the sessions to go over the 100 gig compared to 10. This is not exact science. This is not multi-link PPP, right? It is 10 times more of the session, right? So we could be unlucky, right? It could be a very fat flow there and an unfat flow there. I can't fix that for you. But with this technology here, under a limited time, you can actually have variable speed in your network. And people, what dumbass do that? You should believe me how many situations there are in the data center where actually this is a fact. Due to the fact something is breaking down or something is misconfigured, and you can always fix this. So that's the proof of the pudding on that. Wow, these is really nice colors. So let's talk about burst. How many of you guys believe in buffering, that switch should have a buffer? Do you don't count? Who believes that the buffer should be small in a switch or a router? There's one dude. So one of the problems here is that has nothing to do with congestion. That is essentially the speed of laning, right? If you have a 10 gig port, it is 9.6 nanoseconds between the packets, right? If you have 1 gig port, it is 10 times longer distance, right? So even if you don't have congestion, but you're close to line rate, due to the fact of physics, there will be a lot of packets that are going to go in there because it's just a different lane, right? This has nothing to do with congestion. This is pure physics, right? This is called microburst. Actually, the only thing to solve this is have a decent amount of buffer. Core routing guys has known this for 30 years because they could have one interface that were FTDI, one were token ring, and one were Ethernet, right? So there were inbuilt there a difference in the media and probably a difference in how you fluctuate ring to when you're going to stuff packets out. For some unspoken reason, switch guys have never cared. So usually if you take a switch straight, they can have those fantastic gigs of 1.8 meg. That is not even a 1500 byte packet. They can have 10 megs. 10 megs, even if you say it's a shared buffer, that at best is roughly 1 or 2 milliseconds on one port. So the only thing to solve this stuff is essentially having a buffer. I don't say you can drop packet, right? In order, because that you want to have fluctuate with the TCP, you want to pull down the windowing so that the congestion window and the senders go down, right? That's good. That's good between you and me, right? When I'm accessing, Googling something and getting something, if they pull down my rate, that's not the end of the world, right? The problem in a data center is that that is the minor part of the traffic. The big chunk of the traffic in a data center today actually never leaves the data center. For instance, storage. And without storage, nothing happens. And you can't drop storage. You simply can't drop storage. Because that is the data. That is the data that they're going to create. So if Pedro goes to Google or eBay or whatever, going to buy his fancy pink shirts that I hate, actually, there's a lot of service that incorporate to create the response back, right? That's the east and west traffic. That's the traffic that you can't drop. You can drop the response to Pedro. That's not the end of the world, because there are 1 million more Pedro probably, right? But you can't drop the east and west traffic. You can't drop the storage. If you're doing that, well, then you sacrifice performance. I'm not going to hug you, dude, on the buffering. I trust that you're honest, actually. So you have a beer with me later on in the evening. So we have done lots of testing in that. So obviously we are callers, right? So this is one of the tests that I used to do in front of my customer, and people actually wanted me fired for doing it, because what we're doing is we take one of our product line that is Trident-based, T2, it has 12 megs of buffer, roughly 8 of them are in a shared pool, rest of them is in ingress and egress per port, because you need to have some buffering to even build a packet, right? And then you do some burst on it. I don't even saturate. So in this case, we have 50% incoming on 2 interface, so it just amount line rate on the outgoing interface. Just amount of line rate on the interface. And in the first scenario, we actually don't drop that much, right? But that is not how network looks like, right? Network and TCP are a combination of burst. So if you send the same amount of packet over 5 seconds, but you send them in burst, you can see on the shallow one, massive amount of drops, because at best, 8 meg, if that port claims all the 8 meg, at best it can go up to 2 milliseconds of buffering, and then it starts to drop. So essentially it can't handle the burst. We don't talk about QoS here. We're talking about absorbing the natural behavior of TCP. So if you run up Jericho and Qumran product line, which have between 3 or 4 gig of buffer, plus they have solidification, which means actually they have a smartness, so a 1500 byte packet can actually not interfere with a 64 byte packet, stuck between a long train concept. Then no drops, because the burst gets shut out by that you have a buffer. Why do I talk about that? In an exchange point, what type of contracts do you sell? Are all of them 10 gig? Are all of them 100 gig? No, there will be 100 meg, 1 gig, 10 gig, and 100 gig. What is that? That's speed mismatch. That's microburst. The only way to solve it with performance without having customers are pissed, buffers. That's it. Trust me. And ask any of the other guys here that try to do shallow buffers if the customer are happy or not. Right. Since I'm a vendor, Arista has some customers here. Go to them tonight, have a beer with them, ask them what's good about Arista, ask them what's bad about Arista, ask them how Peter is. 2 minutes, thank you. Oh, geez. All right. And by the way, Deere had 2 customers. By the way, he seems to be everywhere, right? So that's it, and Rasmus also. So why not? I mean, if you build an exchange point, right, you should always ask the guys that are doing it, right? And of course, I have an opinion, but the best opinion is always the customer. All right, questions?
Do we have any questions? Really?
Jesus Christ. Usually no one likes me, actually.
Hello?
Julian, do you have a question? No MPLS or traffic engineering? Nothing? No?
Well,
all right.
That was fast.
That was fast, right?
Yeah.
Was it good? Was it? Did he give you some information? Was it horrible? Anyone that says it's horrible, I will buy them beer also. I'm not that difficult. All right,
well,
thanks, guys.
Please give him an applause. It was really great.